Hello everyone, and welcome to today's Chem lesson. Today we are going to spend some time talking about the metric system and scientific notation, two things that are pretty much going to be the baseline for any number we look at in chemistry from now until the end of the year. Now, the metric system should be something that's fairly familiar to a lot of you. Right? You've used it in science classes, you've seen it used in certain aspects of life, but you likely don't have a ton of information on it. The metric system is a lot better than the imperial system because the imperial system, well, let's be honest, it's just not good. Right? For length, we have inches and feet and yards and miles, and there's no consistent way to get from one to the other. We have a totally different system for volume, right? When we talk about pints and cups and liters and gallons, right? We have a totally different system for mass in terms of ounces and pounds and tons, right? They're all different and they're all not good. Whereas the metric system uses one set of prefixes no matter what thing you're measuring, right? If I say a millimeter, and then a milligram, and then a milliliter, you know that in each of those cases, a milli something is a thousandth of that substance, right? A milliliter is a thousandth of a liter. A milligram is a thousandth of a gram, right? It's standardized across everything. And they work in these beautiful increments, right? These beautiful factors of 10. Right? A decagram is 10 grams. It's 10 times whatever the substance is. Right? A kilogram is 1,000 times whatever the substance is. A centigram is 100th of whatever the substance is. Right? It doesn't matter what we put at the end. The prefix in the front is going to tell us the scale of these measurements. Right, so it gives us this nice, clean, easy to keep track of method for any measurement across the board. Right? We don't need to learn a brand new set of prefixes when we start talking about volume, or a brand new set of prefixes when we start talking about energy. Right? They're all the same prefixes. We're going to take a look at this in a little bit more detail in a second, but before we do that, I want to take a little bit of time to also mention scientific notation. Scientific notation is another really important thing when we talk about numbers in chemistry, and also just numbers in science. Right? When we have a really, really big number, or a really, really small number, right, if I have 6 trillion, right, or if I have a teeny, 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 tiny number, these are hard numbers to keep track of. Right? These are numbers that we would like to have easier ways to write and easier ways to read and easier ways to tell exactly how big or exactly how small they are. And that's where scientific notation comes into play. The whole point of scientific notation is to take the big unwieldy numbers and kind of shrink them down into something that's more bite-sized. Right? For example, here I would move my decimal place until it is in this position. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 places to the left. That would give me 6 times 10 to the 13th. Right, this is an easier number to keep track of. I can look right here at the exponent to see how big it is exactly. And I don't need to write 13 zeros. Right? What if I'm writing this number 100 times and I leave out one of the zeros? Then all of a sudden it's a very different number. where I add an extra 0 by mistake. Again, a very different number. Right, so something to remember, when you're taking a big number, right, a number bigger than 1, into scientific notation, you put a positive exponent. When I'm working with a small number like this other one, I'm going to get a negative exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, 5.0 times 10 to the negative 11th. Right, this negative 11 lets me know the scale as well, and it lets me know that it's a number smaller than 0. Right, so if I'm taking the decimal and moving it to the left, I'm getting a positive exponent. If I'm moving it to the right, I'm getting a negative exponent. Right? For correct scientific notation, you need to have a leading number that is between 1 and 10. Right? So a single digit before the decimal. Right? 1.03. That's great. That's good. 6.02. Also fine. Good. But here when we see 10.3, that is bad. You want a single digit before the decimal place. Right? We have control of where that decimal point lands, so ending up with something that says 10.3 is just sloppy scientific notation. The last bit of important information that we want to talk about with scientific notation has to do with really, really big numbers. Right? For example, if I had 5983216928417000000. That is a big, gigantic number. And when I put this into scientific notation, I'm going to take my decimal point and move it until it gets right there. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 places. That gives me 5.9832169284117 times 10 to the 18th. That's not necessarily a better number than what I had before. Right? It's pretty much exactly the same length as the one I had before. And that brings us to this little unspoken bit of information. Right? You don't want to round a number in scientific notation unless you have a lot of digits in the leading number, right? Unless it goes past the thousandths place. So here I've got 5.983. I would want to cut it off right there. 2 rounds down, so all of this just gets wiped away, giving me 5.983 times 10 to the 18th. Right, a much cleaner number than the one I have up here, and doing the entire point of scientific notation, which is to take these big, crazy, unwieldy numbers and make them usable. Now, let's put those two ideas together. Right, let's take scientific notation and the metric system and combine them and see what we get. And here we get all of our prefixes and their scientific notation scales. Right, some of these are going to be familiar, right? When you talk about kilo, mega, and giga, those are things that we use to talk about data size, right? A kilobyte, a megabyte, a gigabyte, a terabyte. Right, those are sort of familiar. We've sort of used them before. Right, here we have centi and milli, right? Familiar ones from any elementary or middle school science. Right, but then we get into the really small ones. And when we're talking about chemistry, we're talking about atoms, which are as teeny tiny as you can get. And so we need these pico, nano, and micro, these prefixes, to talk about things like how big an atom is, how heavy an atom is. And we see, right, a hundredth for centi, a thousandth for milli, a millionth for micro, a billionth, a trillionth. Right, getting smaller and smaller. And these things are all on reference table C. All right, so let's take a look at reference table C. All right. This is exactly what is told to you on table C. I cut and paste this directly out of our reference table. It gives us a bunch of our prefixes, it gives us the symbols that we would use to talk about those prefixes, and it gives you the factor that we would use for these prefixes. And the sentence that's important here, the way we're going to read this, is one prefix unit is equal to factor units. Right, so let's make that a little bit more common, right? If I'd said, let's take kilo as the example. 1 kilogram is equal to 10 to the third grams. Right? 10 to the third is 1,000. Right, so 1 kilogram is equal to 1,000 grams. And I can take whatever unit I want and put it into that blank spot. Right, grams, liters, meters, joules, lumens. Right, doesn't matter what I choose to put in there. This is always true. Right, 1 kilo is equal to the factor. Right, so one prefix is equal to this number. Right, what if I were to choose milli? Right, 1 milli something is equal to 10 to the negative 3. So that's a thousandth of a substance, right? Which is the same that we get here where I told you what it was. Right, a milligram is equal to 1,000th of a gram. A millimeter is equal to 1,000th of a meter. And these are on the reference table for you. They're there for you to see. They're there for you to use. All right, let's try a couple of practice problems. Right, if this number were going to be put into scientific notation, which one is correct? I'm going to put about 20 seconds on the clock here. If you need more time, pause the video and then hit play again. So here, when we're looking at this number, we want to put it into scientific notation. We know the decimal point is back here, and we want to move it over until we get here. So we're going to move 3, 6, 9, 12 spots, right? Making choice 1 the correct answer, right? 1.47 times 10 to the 12th, which is how many spots we had to move the decimal to the left. You could also keep in mind that you need a number between 1 and 10 as your leading number. 14, not between 1 and 10. 147, not between 1 and 10. Right, making 1 the only correct scientific notation, on top of it being the correct answer. What about this one? 170 grams is equal to how many kilograms? So here, the correct answer is choice 2. If we looked at table C, it tells us 1 kilo something is equal to 1,000 of that unit, right? So 1,000 kilo or 1,000 grams is equal to 1 kilogram. Right? This, choice 1, is a factor of 100, right? This is 100 times smaller. That's not to the scale of 1,000, right? This is 1,000 times bigger, and this is 1,000 times smaller, right? So in this case, 1 kilogram is 1,000 times bigger. So if we have grams, we want to make it 1,000 times smaller, making choice 2 our correct answer. What about this one? Taking this number and putting it into scientific notation. In this case, I'll tell you there are 9 zeros. So you don't have to count them out, right? You've got a decimal there, 9 zeros, and then the number 3. So which one is the correct scientific notation? Okay, good. I see in the chat a lot of people getting it right. Choice 3 is our correct answer. Right, you have to move the decimal 9 times, then 1 more. So you can get 3 times 10 to the negative 10th, right? A number smaller than 0 is going to have a negative exponent. One more. How many joules are equivalent to 35 kilojoules? Right here again, we're looking at kilo versus the basic unit. So here we're looking at almost the same question we saw before, except instead of a number of joules and we're asking how many kilojoules, we're doing the reverse. We can still use table C to remind us that 1 kilo is equal to 1,000, not kilo. All right, 1 kilo something is 1,000 regular somethings, so 35 kilojoules should be equal to 35,000 joules. All right, making choice for our correct answer. And from here, I'm actually going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.